Hello everyone. In the last class, we have seen what is mean by Gauss map. Gauss map is a mapping from S to Sn, where S is the end oriented end surface, and Sn is the end sphere, unit end sphere. So in today you are going to see a important theorem that says that Gauss map is an onto map. So theorem states that let S be a compact connected oriented end surface. Remember this, only in the case of a compact connected oriented end surface this property exists. Okay, so it is a compact connected end surface already given, exhibited as a level set f inverse of c, that is S is equal to f inverse of c of a smooth function f from Rn plus 1 to r with del f of p not equal to 0 for all p element of S, then Gauss map maps S onto the unit sphere Sn. So you have to show that Gauss map is onto. To prove onto, what you have to do, you have to take an element from Sn and you have to find a unique element that corresponds to that corresponds in S. Like for one element you take from Sn, you have to get a corresponding element in S. That's the way to prove onto. So here what you will do, let us see how to do this. I have given a figure here. You have a geometry that you have to consider before start. Here this is your Sn, okay, and this is your S, and you have to consider one point of Sn. This is the V point I have taken from Sn. You can take any point, this is the one point taken. So corresponding to this point you have to find a point on S. That's our aim. So if you take this point V, then you can take the vector corresponding to that, that is this is the V bar vector from the origin, and then this line represents the perpendicular, right, that we can write it as V perp. V perp will be a plane, n plane, correct. This is a unit vector and this will come n plane. So n plane if you have, and if you move this n plane throughout this, what will happen, here is your n surface and it will touch somewhere, right. Either it will go like that, and sometimes this figure can be on this side or this side, anywhere it can come. So when you move this, if you move this it will touch here, and if you move away from this figure and when you come back it will touch here, right. So if it come back it will touch here. Come back means this is the direction of V you are moving, and if you are coming back it will be the opposite direction of V, correct. So this is in the opposite direction and this is in the direction of V. The normals comes for normals at these 2 points I am telling. So ultimately how many points you will get, you will get 2 points at which this V perp will touch the end surface. Why? This is a compact figure, so it will touch definitely at 2 points. It will have maximum and minimum. For a continuous map in a compact space you will get a maximum value and minimum value. So you will get 2 points at which it touches the derivative, the tangent, it will comes at these 2 points, same thing, right. So how you are getting that, you are moving this V perp to infinitely far away from this S, and you are coming back, you will touch some point here, and if you are again if you are just moving towards S, it will touch somewhere here, right. And in two ways it will touch here, one in this direction, one in this direction, it can come. Whatever you will touch the figure at 2 point only, and suppose at 2 point only, that 2 points you can say as P and Q. Okay, so here the idea is, what you are going to say is, corresponding to this V I can either take P or Q. That's what I am going to say. To make it clear, what you have to do, corresponding to this V, this is the vector you have, you will get only one point at which this vector comes. If it's coming in more than one place, it will not be onto, correct. If you have the same vector at more than one place, what will happen, you will have corresponding to this V, you will have 2 points, so it will not be onto then. So corresponding to this point you should get only one normal vector, then only you can say that it is onto. So it can be in a positive and negative direction. This is the positive, negative is in this direction, right. So you are getting this, and 2 points at which this end plane touches, so in that one point only corresponds to this v. That's what we are going to say. Okay, now how to do this? For this, let us have a function definition first. I'm going to define a g of p. I'm going to define in such a way that p dot v, where p is an element from your capital S and v is an element vector from, v is a vector from, or v is an yes, v is a vector, or you can say, rather you can say like this: V is an element of Sn. This is the n surface. V is a vector, okay, and that can be written as V equal to some p comma V. I can write, okay. So at which point it comes at the p, what is the vector v? That's only the case, okay. So this is the way I am going to define my g of p. So what it will come actually, if I take my v as a1 a2 etc an, we are taking one point from S and that point is a1 a2 etc an plus 1, sorry, not an plus 1, an plus 1, okay. So this is an element of Sn, okay. So how can you write this then? G of p can be written as g of p is equal to p dot v, right? P dot v means what it will come? This will come as p is x1 x2 etc xn plus 1, v is a1 a2 etc an plus 1. When you take the dot product, you will get a1 x1 plus etc plus an plus 1 xn plus 1. This is equation of a n plane, correct? So G represents level sets of G are n planes that will be parallel to what? Parallel to your V perp. So this represents level sets, okay. Level sets of G are n planes, that you remember. Now here you are restricting your G to where S, right? S to R you are restricting, then it will have a maximum point and minimum point. Let us see P and Q are maximum and minimum points at which it attains its maximum or minimum respectively. Then by Lagrange multiply theorem, what you can say? You can say that del G is equal to lambda del f, correct? Del g is equal to lambda del f. So what you can say, or del g of p, rather you can write del g of p for p element of S, okay. P element of uh, p element of S, okay. So you can write this, what is del g of p? Del g of p is equal to p comma derivative with respect to x1 x2 etc xn plus 1, that will come a1 etc an plus 1, right? See, your g is this. When you find derivative with respect to x1, a1 will come, derivative with respect to x2, a2 will come. Likewise you will get in this way. This is same as what? P comma your v, that you can write it as v bar. So here del f of p, how can you write? Del f of p equal to, you can write this as, if you consider your n bar of p as del f of p by norm del f of p, what you can write your del f of p as norm del f of p into n bar of p. So I'm going to replace these two over here. So what you will get? V bar is equal to lambda norm del f of p into n bar of p. But we have v bar is coming from where? V is an element of your Sn, so that implies your norm v bar must be equal to 1 because it is a unit sphere, and norm of n bar of p is also equal to 1 because it is a unit normal. That implies that you can say here your n bar of p can be written as this. Both are unit vectors, means it can be plus or minus v bar only. This constant can come plus or minus 1 only, okay. So n bar of p can become as plus or minus v bar. Now and in the similar way, if you consider q also, you will get n bar of q equal to plus or minus v bar. Okay, so at the point P and Q are the maximum and minimum points we have already told. So by Lagrange multiplier theorem, at P and Q, this will be satisfied. So P, we are getting this. In the similar way, if you put Q, you will get n bar of Q will be equal to plus or minus V bar. Now what you have to say? You have to say that n bar of P is not equal to n bar of Q. That is, if n bar of P is plus V bar, n bar of Q must be minus V bar. That's what we have to prove. If it is equal, you will have a contradiction. So it should not be equal. That's what you are going to say. So you are going to find a contradiction by stating some path between this P and Q. So how to do this? So you have to construct a you have to construct a continuous map here. Construct alpha. How to construct alpha? So you have to construct alpha in such a way that some properties should be satisfied. What are that properties that I will write here? The properties that should be alpha I am going to map from closed interval a b to closed interval a b to Rn plus 1. Okay, and this is a continuous map. I'm going to define such a way that first condition it should be satisfied as alpha of a must come as p and alpha of b must come as q. So p and q must be joined by this path. Okay, and with that alpha dot of a must come as alpha dot of a must come as the vector p comma v, and alpha dot of b must come as the vector q comma v. In this way it should come, and second condition should come in such a way that alpha of t must not be an element of S for all t between a and b. Only at the end points, if you find the value of alpha, it should come in S. For all the other, it should be outside S. How to construct such an alpha? So I'll show you. So this is your S you just suppose. Okay, this is your S you just suppose. Now you have to construct such an alpha. I'm going to consider a circle that contains this S. So I'm going to draw a circle around this. I hope it is a circular form. This is a circle S1, and this is your S you just suppose. And this is your point P. So this is the tangent over here. The same tangent I can draw here also. This is the point Q. Okay, and this is the point P you just think. Now I'm going to construct in such a way that this is the vector. Okay, wait. This is V, correct? And this will be minus V then, opposite, right? If this is V and this is will be minus V, correct? Opposite direction. So this path I will name it as alpha 1, and this path I will name it as alpha 2. And from so you are going back, right? So I will make it in another way. The path I'll go in this way. Okay, so this will go in this way. So I'll start from P and I will go by this way and I will come around like this. This is the way I'm going, and I'm going by this way and coming to this and going back to Q this point. So this path I have. So I have a three path continuous path connected. So I will name in such a way that this is going to be alpha 3 and this is alpha 1, and this one I am naming as alpha 2. So alpha 1, alpha 3, alpha 2 together will make a path alpha that connects from P to Q. What is the peculiarity of this? P is coming in S, Q is coming in S. But all the other points that you can see in this path are outside S, correct? So this is a path I am going to define. So how to define this alpha, that you have to see. So I am going to set your alpha 1 of T as, how I will write, a point P plus T into V. So this, okay, and alpha 2 I will set in such a way that Q minus T into V. This is in opposite direction V. If this is V, this is opposite direction V. So minus TV. For this, here it is coming 0 less than or equal to T less than or equal to A1, and for this I'll write 0 less than or equal to T less than or equal to A2. So you just check, when T equal to 0, what will happen? Alpha 1 of 0 will come P, that is starting point. When T equal to 0, alpha 2 of 0 will come as q. Okay, so this is the path I have defined, alpha 1 and alpha 2. Now I am going to define alpha 3. Alpha 3 I am defining in such a way that it's a little bit in other way. Just see, alpha 3 I am going to define from b1. This is another path, right? b1 comma b2. This is closed interval. Okay, from an interval b1 b2 to your s1 I am going to define. Okay, so that how it comes, alpha 3 of b1 must come as which point? This point it should come. Which is this point? This is the end point of your alpha 1. So that is alpha 1 of a1. Correct? And alpha 3 of b2 should come which point? This point, ending point. That means it is coming as your alpha 2 opposite one. The alpha 2 of a2 it should come. So I am defining alpha 1, alpha 2, alpha 3 in such a way that alpha 3 of b1 should come alpha 1 of a1, alpha 3 of b2 should come alpha 2 of a2. That is, this from here to here is your alpha 3, and from here to here is your alpha 1, and from here to here is your alpha 2. So this is clear, I think. So this all are continuous together, it will come a continuous path. So now I define this as a whole as my alpha. So how to define alpha? Now let us see. So alpha of t I am going to define in such a way that alpha 1 of it will come alpha 1 of t, alpha 1 of t, and here I will write the interval as 0 less than or equal to t less than or equal to a1. That is, in this path, in this interval, your alpha will give you this path. And next, alpha 3 of t plus b1 minus a1, where the interval is a1 less than or equal to t less than or equal to a1 plus b2 minus b1, and alpha 2 of b a1 plus a2 plus b2 minus b1 minus t for what is the interval a1 plus b2 minus b1, this one, less than or equal to t less than or equal to, what you have to write, a1 plus a2 plus b2 minus b1, this one. Then only if you substitute for t you will get 0 here. That alpha 2 of 0 will give you the ending point q. So when t equal to 0, alpha 1 of 0, that will come p. When t equal to this value, you will get alpha 2 of 0, that is q, and all the other values will be followed. Here you can see alpha 1 of a1 will give you alpha 3 of b2. When you give here a1, what will happen? Alpha 3 of b1 will come. So these 2 points two are equal. So it is continuity we are telling. And when you put this point here, you will get alpha 3 of b2, and will give you this point over here, you will get alpha 2 of b2. So that 2 points are equal. So in the same, alpha 2 of a2, sorry. So these 2 points are equal, and when you give this point, you will get alpha 2 of 0. That means you are getting a path from p to q. So these 2 points are also matching with this mapping. So alpha of t can be defined in this way, so that you will get what you will get. The starting point is this and ending point is this. This is your a and b. Okay, this is your a and this is your b. So you are getting alpha of 0 is coming as p, and alpha of this, what is that, a1 plus a2 plus b2 minus b1 is coming as your q. That was our aim, what I have told, this, right? Here instead of a we are getting 0, we are defining, and instead of b I am defining, this is the point. So at that point you are getting q. Now when you get alpha dot of 0, what is alpha dot of 0? At that point, when you find the derivative, you will get the tangent vector. That is what here, this one, right? Derivative of this. And here also what you will get when you find the derivative, alpha dot of 0, it is coming, means you have to find alpha 1 dot of 0, that will come as v, right? So you will get here it as v, you will get, and alpha dot of a1 plus a2 plus b2 minus b1 will give you, this is point here, and you have to find derivative alpha dot here, alpha 2 dot. So alpha 2 dot will give you q, sorry, alpha 2 dot will give you minus v, correct? it will come minus v. So that is coming same as what your other point, that is again coming here. It you can write p comma v, and this will come q comma v. Okay, this will come q comma v. So all the conditions are satisfied, and this is also satisfied. I told this is coming outside, right, outside s, so this are also satisfied. Here a and b, what is a and b? A is 0 and b is, this is the value for b. Okay, this is the value for a, that you remember. So this is the alpha of t you have constructed. So by using this continuous map, you are going to say that your n of p and n of q must be different. Okay, that is you are going to see. So I'm going to come to a contradiction by taking it as equal first. So let us suppose that n of p and n of q are equal, and let us take n of p equal to n of q. Okay, equal to del f by norm del f plus value. Okay, it is a plus value. Let us take in that. Then f circle alpha whole dashed of a. What is a? A is here 0. Okay, this is equal to del f of alpha of a dot alpha dot of a. This is equal to what you can write. This can be written as, from here you can write, if you consider p case first, you will get del f of p into n bar of p dot alpha dot of a is same as your vector v at p. Okay, in the similar way you can write case of b also, that is f circle alpha dashed of b will come in case of q. So you will write it as del f of q into n bar of q dot v, the same. Okay, and so the if the derivatives has, if this n bar has same sign, if n of p and n of q have the same sign, what will happen? F circle alpha dash of a and f circle alpha dash of b will have the same sign. I told this will come plus or minus n bar of p and n bar of q. What do you have got here? Just see. Here it is a plus or minus v. If it is same sign, when you take the dot product, both will be plus or both will be minus, correct? So this will be either plus or minus if these two are equal. So what will happen? If it is equal, then both this derivative will have same sign. So what will happen if it has same sign? Either it will be increasing or decreasing, right? We know at extreme points, if the derivative is coming greater than 0 or less than 0, what will happen? So if it has same sign, a positive sign or negative sign, depending on it will be increasing or decreasing, we are telling, right? So if it has same sign, you can say that f of alpha of a equal to f of alpha of b equal to c, we know. And then by intermediate value theorem, what you can say, there exists a there exists t1 comma t2 element of open interval a comma b, such that there exists some point at which it comes, so one point it will come greater than 0 and one point it will be less than 0, by this definition, right? So you can say that f circle alpha of t1 is coming greater than c, and f circle alpha of t2 is coming less than c, we can take. Okay, at some point it will be coming greater than c, at some point it will come less than c, that we can say. If this hope you remember this concept, like f of alpha of a equal to f of alpha of b equal to c. Why this is coming? Alpha of a and alpha of b are elements of your n surface s, correct? So this will come equal to c. Then there exists t1 and t2 in between a and b, such that at some point it should come greater than c and at some point it should come less than c. Then by intermediate value theorem, what you will get? You will get a value in between t1 and t2, such that what you can write, then there exists t3 in between t1 and t2, such that you can say that f of alpha of t3 must be equal to c. That means alpha of T3 is an element of S. What is T3? T3 is an element of A comma B. Why? T1 and T2 are inside AB, so T3 is in between T1 T1 and T2 implies T3 will come inside A and B. This is a contradiction. We have told alpha of T3 will be not an element of S for any element between A and B. So this is a contradiction. Which is contradiction. Okay, which is a contradiction to 2, right, which is the statement 2, second statement. Therefore what you can say, n of p is not equal to n of q. If you take del f instead of here what we have taken here, taken plus in the place, if you take minus, the same result it will follow, right? So in both case you will get n of p not equal to n of q, since we are coming to a contradiction if you take it as equal. Therefore what you are getting, for each V element of Sn, there exists a P element of S with N of P equal to V, plus or minus V, any one of plus or minus V. Only such one point only you will get from S, corresponding to a V element of Sn, which says that Gauss map is on 2. Hope you understood how it is proved. This is very important theorem. Once again, just go through the construction what we have done in the theorem. First, what we have done, we have defined an end plane by the map G. And why we have taken this, we have to apply Lagrange's multiplier theorem here. Why we are using Lagrange multiplier theorem? Because our given end surface is a compact connected figure, it will have a maximum or minimum value for definite, right? So if you define a G in such a way that your V is coming from Sn, then we are considering V bar, the vector V bar, with a point P from your end surface S. P and Q we are choosing in such a way that it just touches V perp, right? You will get 2 points in such a way because this is a compact figure. So you are defining G and we are restricting G to this end surface S, oriented end surface S. And P and Q are the point of maxima or minima you just take because it is compact. Now by Lagrange multiplier theorem you can write in this format. So you will get it as v bar is equal to lambda norm del f of p into n bar of p. That means your n of p must be equal to plus or minus v, because n and v both are unit vectors. So this is plus or minus v. In the similar way, if you consider q, you will get n of q equal to plus or minus v. Then we have to show that n of p and n of q will never be equal. It will be either plus or minus, either plus v, then other will be minus v. That's what we have to show. So for that we have to construct a continuous map. We have constructed an alpha from AB to Rn plus 1. Your A you are taking as 0 and B you are constructed in such a way that B will come as A1 plus A2 plus B2 minus B1. This is the construction. For constructing alpha we have constructed 3 path, alpha 1, alpha 2, alpha 3 in this way by containing S in a circle, perfect circle. This is possible because this is a compact figure. So we have constructed in this way such that alpha 1 of 0 will come as P and alpha 2 of 0 will come as Q. So you have connected it with alpha 1, alpha 3 and alpha 2, make an alpha, so that alpha of 0, alpha of that first point 0 will come as your P and alpha of the end point will come as your B. So first point coming as your A and last point will come as your B, and you are constructed so that alpha of A will come as P and alpha of B will come as Q, and derivative at that points will come P comma V and Q comma V. Okay, derivatives will come in that way. So with that, or one more thing you can say that alpha of t will never be element of S for all t other than these two endpoints. So all the points will come lies outside the S, that also is satisfied. So this construction we have, using this construction what you are going to do is you are taking your n of p, n of q, both are same. You are just taking like minus del f of del f by norm del f or plus del f by anyone normal orientation you are taking. So if you take consider plus first, then f circle alpha dash of a equal to, write, you can write in this way, you can write in this format, and n of p and n of e, if you take a dot product, will get either plus or minus 1. So if you take if you have n of p and n of q are of same sign, both this will come, that is f circle alpha dash of a and f circle alpha dash of b will have same sign. If it have same sign, both will be increasing or both will be decreasing. But here you just see f of alpha of a equal to f of alpha of b equal to some constant c. Then there exists t1 and t2 in between a and b, such that what you can say, at that some point t1 it will come greater than c, at some point t2 it will come less than c. So what will happen by intermediate value theorem? There exists a t3 in between t1 and t2, such that f circle alpha of t3 will come as c. This implies alpha of t3 is an element of S, right? So alpha of alpha 3 element of f inverse of c, that is contained in S, so it is element of S. So which is a contradiction to our construction, right? We have constructed alpha in such a way that this f of alpha of t3 is not an element of S for any t between a and b. So which this contradiction happened because we have taken n of p and n of q are of yes, n of p and n of q are of same sign. That's why we are getting a contradiction. That means you have a different value for n of p and n of q. So that means corresponding to v element of Sn, there exists one p in your oriented n sub S with n of p equal to either plus v or minus v. If you take the other extreme q, you will get either plus v or minus, just opposite of that. Only one point you will get corresponding to 1 v in Sn. Hence the Gauss map is onto. Hope you got some idea of the theorem. Just go through 3 times and write down the notes clearly. And it is almost same from the text. Everything is written in the text as it is, the steps and all. So you may write the same things from the text itself as the proof. If you have any doubt, you may free to contact, and we can clear that in a discussion session or anything if it is required. That's all for today. Thank you.